This lecture is about aerodynamics. Aerodynamics is part of fluid dynamics. It relates to the action and reaction of a body moving through an airflow. Right? Now, one could argue, where do we apply aerodynamics? Now, aerodynamics is applied on machines such as aircraft, space shuttle, Formula One cars, golf balls, racing bikes, wind tunnel, parachutes, flying boats, including sea skimmer and encranoplan, which is normally used by the Russians. Right. Now, we've mentioned about different machines, but on this occasion, we're going to restrict the lecture on aircraft only so that we can review the composition of the air around the aeroplane. So let's consider the changes which occur within the atmosphere and learn how those changes can affect the interaction of a solid body moving through the air. Right. Now, before we talk about the aircraft, we should know the component part of an aircraft. Now, what do I mean by knowing the component part of the aircraft? Because we have a young man, right, a layman who don't know anything about the aircraft. So we need to introduce them, right, so that they could learn about how the aircraft component parts, how they work. So to start with, we have the cone of the aircraft, which is the very tip of the aircraft. And then we have the fuselage, the actual body, that's the fuselage. And then we have the aerofoils. When we talk about aerofoils, we mean the wings. The wings are the aerofoils. Now, these wings is also known as the main plane. And the main plane are the ones which house the engines. So we're talking about the engine pylons where the aerofoils are installed. So on the aerofoils, we have the flaps, we have the ailerons, right? We have the winglets, and then we have the leading edge. So these are the aerofoils. Now we need to talk about the empennage section of the aircraft, meaning the back side of the aircraft. So the back of the aircraft, which comprises of vertical stabilizer, the rudder, horizontal stabilizer, the elevators, right, and then the tail cone. This section is known as the empennage. Now, for a glitch of a hiccup, let me go over the component parts again. So we have the nose cone, we have the fuselage, which is the body of the aircraft, we have the aerofoils, which is also known as the main plane. The aerofoils is where the flaps are installed. We have the inboard flaps and then the outboard flaps. And at the very tip of the aerofoils, we have the ailerons. Now, after the ailerons, you have the winglets. The winglets are installed on the aircraft to cause separation of the flow. Then we move to the back of the aircraft. There we have the vertical stabilizer, which is known as the fin. We have the rudder, we have the horizontal stabilizer, and then we have the elevators. Now, basic aerodynamics explains the terminology with the fact that air is able to lift heavy objects, meaning the aircraft. For an aircraft to be aerodynamically stable all the forces acting on the aircraft has to be in equilibrium. To achieve top performance, the aircraft has to have good characteristics, endurance, and optimization. So for the aircraft to be aerodynamically efficient, in order for you to get more acquaintance with the aircraft, you need to know the physics of the atmosphere. Now, when we talk about the physics of the atmosphere, we're talking about the mixture of gases. So, to know vehemently about how the gases are divided in composition, we have 78% nitrogen, right? 21% oxygen, and then 1% other, which including carbon dioxide, krypton, neon. All these are part of the 1%. This ratio remains constant regardless of altitude, right? And air pressure decreases with an increase in altitude. Atmospheric pressure is the pressure exerted at the surface of a body by a column of air in an atmosphere. So the pressure varies both with altitude and weather patterns. Now, standard is an average atmospheric pressure at sea level and is defined as 1 atmosphere on Earth. That is why all aircraft readings is taken on a sea level so that we can have a uniform standard, right, for aviation. Now, one could be asking, if that is the case, then we need to know the relationship between International Civil Aeronautical Organization standards, right, and then measurement taken from the sea level. So they have agreed on standard as a reference for all aerodynamic calculations. These standards are used to compare flights, right, including the engine performance checks relative to similar aircraft and equipment, regardless of where the readings were taken. So international standard atmosphere, right? The standard settings are based on air pressure, air temperature, air density, and air humidity, right? Regardless of local conditions. Now, based on this, we need to know about the relationship between the ISA, right, and then the local speed of sound. Now, how do we work out local speed of sound? Well, you need a formula, and the formula for working out local speed of sound is A equals gamma times gas constant times temperature. And gamma is 1.4, gas constant is 287, temperature is 273. Now, you need to take the local humidity, local temperature into consideration. But whether it's 15, 20, whatever it is, you added the 273. In this occasion, we assume it's 15, so we added 273 to 15, making 288. Now, by multiplying gamma times gas constant times temperature, the local speed of sound we get here is 340 meters per second. Now, ladies and gentlemen, that brings to the end of this presentation. And thank you very much. So next week, we'll be looking into another presentation where it talks about aircraft stability. Thank you.